It's a great pleasure to be here at this first conference on quantum energy. It's a pretty exciting set of subjects we're going to hear about. I'm just going to set my timer here so I don't delay you from getting to copy, which I'm sure would be a terrible thing to do. The subject of my talk is how quantum mechanics will impact the next generation of learning machines. Note the order, learning machines. So learning machines, like any machine, satisfy this particular definition. They're open dissipative systems driven into non-thermal equilibrium steady states by access to a low entropy source of energy. That's not terribly informative. Here's an example of a learning machine. I used to own this. Her name was Rosie. Unfortunately, Rosie went the way of most of her other sisters. But if you remember nothing else from this talk, remember this. There are billions of learning machines on this planet, and none of them was programmed to optimize the cost function. They were all designed and constrained by the laws of thermodynamics in this particular case. So let's move on a little bit and see what extra we need to add if we're going to build artificial learning machines. First of all, we need sensors and actuators, but that, of course, will not be enough. A learning machine is something quite distinct, and the easiest way to see that is to realize that this is not a learning machine, I hope. So this is one of those robotic vacuum cleaners. I'm pretty sure it's not accessing the internet when I'm out and watching television and ordering, well, I haven't seen any pizza boxes. It just wanders around cleaning the floor because it has actuators and sensors. It's not much more than a thermostat on steroids. We need to add another component. However, I would point out that motility is perhaps the most important actuator of all. Just moving around and changing your sensations is enough to drive learning machines. In fact, every biological learning machine, that is every biological system with a central nervous system, is mobile. In fact, there are various biological organisms which have a central nervous system in their larval stage, but they eat it once they settle down onto a rock somewhere or other because they no longer need it, because they're no longer moving. So this is the design schematics of the kind of embedded learning machine I want to talk about. It has sensors and actuators. These are irreversible physical devices. Actuators do work on the world, therefore their free energy decreases, and sensors have work done upon them by the world and their free energy increases. And there's another machine here which I'll come back to towards the end of the talk to tell you what's in the box. But one thing is for sure, it is necessarily dissipative and must produce heat. It is a fundamental fact that learning has to be dissipative and has to produce heat, and I'll explain why as I go. Now, first of all, you'll have noticed, and I tried to stress, I'm talking about learning machines. Well, at the moment in the literature, in the press, and the news, there's much talk about machine learning. These are algorithms. Of course, they have to run on some machine, and so I'm not going to be talking about the thermodynamics of algorithms. That would be a little bit like talking about the taste of cheesecake recipes rather than the taste of cheesecakes. It's not the same thing. So deep learning neural networks are essentially programs that write programs. They run on conventional CMOS devices, usually, and there is a thermodynamic cost to that because of the devices on which they run them. They don't have to run them on CMOS devices, but they do because that's what they've got. And you can very quickly work it out. I'm sure you've seen many of these comparisons. Kathy just gave one. Running ChatGPT costs around 10 megawatt hours of energy, which, amazingly enough, is the per capita energy consumption of Australia in so one Australian in a year on average consumes about one run of ChatGPT. Slightly disturbing. Clearly there's something wrong. Now, if we go even further and look at the training costs involved in these various large language models, these generative pre-trained transformer models, you can see that as time has gone on, the training cost just to pay the power bills is now heading up towards $10 million US. So it's no surprise that only big corporations are in this business because they're the only ones who can foot the bill. You can see what the problem is. On standard CMOS devices, there's about 10 to 11, many more on NVIDIA GPU chips. Clock rate at 1 to 10 gigahertz, switching energy about 10 to the minus 17 joules in each transistor. So the H100 processor, the go-to processor for artificial intelligence, a company like GPT would have getting up to 100,000 of these devices. It's consuming about 1,000 watts of power for one chip. However, the CMOS, the people building these devices know that this is unsustainable, and IBM recently announced just this year the IBM North Pole chip, which changes the paradigm for computing, classical computing completely. It departs from the standard von Neumann architecture where programs are stored in memory and moved in and out of a central processor. That leads to the von Neumann bottleneck. The North Pole chip has quite a very different configurations. Too much detail on this slide. I just wanted to point out to you what's going on here. A break from von Neumann's circuit-based architecture. Very important, and a very important lesson for anybody doing quantum computing. Here's the energy costs of the North Pole chip. All the NVIDIA stuff is down there in the bottom left-hand corner, and performance of the North Pole chip is up there in the top right-hand corner. So there's a huge amount to be gained by rethinking computation, classical computation along these lines. In fact, just while I was sitting listening to Kathy, I got a message from my go-to AI app, Perplexity, telling me that Sam Altman is now backing a new company called Rain Neuromorphics, which is building a non-von Neumann machine, a neuromorphic quantum computer to try and compete with IBM's North Pole chip. It's a purely analog device, very important, as is a cow, by the way, and as are we. So how much power does the human brain consume? 20 watts, which is about the same power as consumed by the iPhone 15. So this raises the question of what really is the minimum power you need to do learning, to build a learning machine. If we can do it at 20 watts, ignoring the fact that evolution has probably wasted an unbelievable amount of energy getting to us, then what are really the physical limits to learning? So the first thing to realize is learning machines, not machine learning machines like cows and us are embedded in an entropic gradient. Learning cannot happen at thermal equilibrium. And as I stressed, you need actuators and sensors, but you need more. You need a learning machine. But the first thing to point out about actuators and sensors, and indeed learning machines, as I said, they're necessarily dissipative. And by the fluctuation dissipation theorem, that means they're necessarily subject to noise. Now, in the quantum world, that's bad news. But in the learning world, learning machine world, that's good news. Noise is your friend. In fact, you cannot learn without noise and error. Everybody knows this. We've been hearing about learning by trial and error since probably, I don't know, the first hominid picked up a stone and cracked a nut. So that's extremely important. So let me now just give you a quick argument of why learning is necessarily dissipative. And it goes like this. Here we have a little machine. Its objective is to sort the sheep from the goats, or at least silhouette images of sheep and goats. And we just randomly choose a sheep or a goat and stick it in at one end. And initially, it just comes out randomly in one or the other exit. I'll label one exit the sheep exit and one exit the goat exit. And so initially, it's completely random. But the way it works is that every time I see it come out in the wrong channel, I go back and change the configurations inside the machine by changing bias voltages, moving gates backwards and forwards. I don't mean logic gates, I mean actual gates, like you have in a cattle race. And eventually, you will get it pretty good. You cannot get the error to zero for a fundamental reason, that is, learning requires noise. But before training, the entropy is log 2, because I choose those samples at random. But after training, if the error probability is epsilon, say 10 to the minus 6, the entropy has been dramatically reduced. And if this is being done in a physical device, there's a cost to pay, a thermodynamic cost to pay, which that machine must pay by dissipating heat. So learning is necessarily dissipative. Heat and entropy must be dissipated during training. But as I say, what is the real question is, where is it dissipated, and what is the minimum cost we have to pay? So let me now focus on that. To get to this point, I need to go back to the very beginnings of machine learning, which is McCulloch's and Pitt's idea of the mathematical model of an artificial neuron, a perceptron. It was based on a very poor understanding of mid-20th century neuroscience. Turns out to be a remarkably good idea, despite that. And it's a simple function. Here's an example, a sigmoidal function. And it simply says that you have some input parameter, and if it's too small, too negative, the output is 0. And if it's really big and positive, the output is 1. And it goes from 0 to 1 in some nonlinear fashion. And that's all you need. So in the model of Rosenblatt, the perceptron algorithm, which I stress is an algorithm, this is just a function that's going to be realized in your favorite digital computer. The way it works is you have a bunch of inputs, x1, x2, x3, x4, which could be real numbers or could be binary. You multiply them by some weights, and then you add them all up, and then you stick them through this activation function. and it either comes out with something close to 0 or something close to 1. And so 0 would be exit for sheep, 1 and 1 would be the exit for goats. And then to train it, you just feed back onto the weights and repeat and repeat and repeat. So it turns out this algorithm is incredibly powerful, largely because while Z is a linear function of the inputs, the activation function is highly nonlinear and generates all powers of the input data. So just about anything can be represented that way. In particular, a binary function of 2 numbers can be done this way, and this was a big breakthrough in the early days of machine learning. There are 16 2-bit functions with 1-bit output. You can easily see that if you think about it for a minute, just like there are 4 1-bit functions with 1-bit output. And here's a simple device that Sahar, my former student, I should say, Sahar and I wrote in our paper back last year in Contemporary Physics, showing how you would do it with a neural network with 1 hidden layer with 3 perceptrons. And it turns out you need, let's see, 1, 2, 3, 4, 5, 6 weights and 2 biases, and you feed back onto the weights and biases to get this thing to learn. The most important thing is it can learn XOR, and the way to train it is you initially start off with the weights completely random, so it's just producing binary numbers at random. It's just a coin flip. But every time it makes a mistake, you feed back, and eventually, in the case of XOR, you can show that depending on the slope of the activation function at the origin, you can reduce the error that it makes exponentially small as you train the machine by feeding back onto the weights. Beta tells you something about the slope of the activation function at the origin. In CMOS devices, it will be related to temperature. So this is what a deep neural network architecture is. It's just more of the same. More hidden layers, more weights, and it apparently seems you can do just about anything with such a device. But as I said, I'm not interested in algorithms. I want to talk about machines. So the passage from algorithms to machines just requires replacing the activation function with an activation switch, an actual physical device that turns on or off. It's dissipative and it's subject to noise, so occasionally it switches without you intending it to switch. You do the same thing again, but now you have real physical signals coming on, and you have real physical labels. This is a sheep, this is a goat, this is a 1, this is a -1, and you sum them all up using, I don't know, amplifiers or whatever you like, add them up, send them through the activation function, then you compare the output to the label on a little comparator, and if they're different, you feed back onto the weights. So it's just a standard stochastic control architecture for building a machine. So the classical physical perceptron is where the heat is dissipated. If I build this as a switch, it's a dissipated device. That's the minimum cost of energy. And in a classical device, all the noise in these devices is thermal. It's essentially just Arrhenius-type activation over a barrier. In a quantum perceptron, which I'll come to in a minute, the device operates at very low temperature and is subject only to quantum noise, by which I mean spontaneous emission and quantum tunneling. And those of you interested in quantum computing might ask, where's the entanglement? It's right there. Entanglement is the origin of spontaneous emission and quantum tunneling. Okay, so a physically realized activation switch is a nonlinear dissipative system. Here's a simple example based on a particle in a double well potential under high dissipation. High dissipation means it doesn't, if you change the potential bias, the particle doesn't rattle around backwards and forwards before settling down. It just very rapidly settles to a steady state. So I can put a linear bias force pointing to the left or pointing to the right, and I can change the state of the switch. The weights control the linear bias potential, and the noise changes the shape of the steady state response. As I showed there, you can solve this. Whoops. How do I go back? Oh dear. Where's the back button? That must be it. There's the steady state probability distributions. You'll see it's not perfect because of noise, and there has to be noise or you can't train this thing. So if I look at the steady state response, here's the average value of the coarse grain position of the particle. As I decrease the noise from left to right, you see this switch gets sharper and sharper. I stress that's the steady state response, the infinite time response of this device. What you really need to know is what happens in the time domain. So here's an example of a switch with different level of noise where I change the bias potential over some time scale. And you can see if the noise is really large, 0.7, roughly proportional to KT, everything switches. There are three simulations here. As I decrease the noise, I eventually get to the point where only one switches and two don't. And so what you need to do to learn on this device is you need to optimize the noise in order to optimize the learning rate. So let me explain how that works. As the noise is decreased, the switch is slower, and in the limit of no noise, there is no switching at all. So if you think noise is bad, let's get rid of it, you're sunk, because it will never switch and it will never learn and it can't be trained. First important lesson. Dissipation and noise are essential for learning machines. Now, we're now in the business of what's called stochastic thermodynamic fluctuations. What matters is the fluctuations in work done. Sometimes it'll switch with a little bit of work done because the thermal fluctuation will take you over, and sometimes you'll need a lot of work to make a switch because of just a rare thermal fluctuation may not come along. So this has been studied now for about 20 or 30 years by people like Karl Jarzynski and others, and we now know that the ensemble average of fluctuations in the work is constrained by thermodynamic properties of the stationary states at either end of the change in the bias. This is the famous Jarzynski relation where the change in free energy determines the fluctuations. And this is a remarkable theorem because the left-hand side, you can change the bias however you like. It doesn't matter, fast, slow, quick, whatever. But the right-hand side is always a thermodynamic quantity. So you might think, well, I want to get rid of the noise and I want to reduce the power, so let's just reduce the temperature. Clearly, in a double well like that, the energy dissipated is of order kT. So you think, okay, I'll make it cheaper to run by reducing kT, but now you see the problem. It'll stop switching, so that won't work. So you can lower the temperature to save energy, but the learning rate decreases as the thermal fluctuations are decreased, and this is bad. So, of course, if you're prepared to wait forever to learn one bit of information, you could turn the temperature down and pay a very, very low energy cost, but you may go extinct before you actually learn that it's a bad idea to hunt saber-toothed tigers or something along those lines. So in a thermodynamic setting, energy conservation is important. In a business setting, paying for energy is also an important constraint. If you set out to come up with the world's greatest AI model that consumes terawatts of energy every time you run it, you're going to go broke very quickly. So ultimately, thermodynamic constraints determine the viability of any learning machine. Now, how do we connect fundamental information theoretical properties like error in learning to thermodynamic quantities like heat dissipated, entropy generated, and so on? Now, the first important theorem that links information theory to thermodynamics goes by the name of Landauer's principle. And it simply says that to erase one bit of information, on average, you need to dissipate kT log 2 per bit, where Kb is Boltzmann's constant, T is the temperature of the environment, into which you are dissipating the energy. So here's a simple example based on a double well. How do you erase one bit? Well, you've got to make it impossible for there to be anything other than one outcome. One bit means when I learn the result, I need to set aside a 1 or a 0 someplace to store the result. So the two figures on the left, it could store binary 1, particle on the left, or binary 0, particle on the right. To erase that bit, I just bias it so that for sure it's always on the left. And as I've just discussed, to do that, you do some work on the system, you wait for thermal fluctuations to take you over the barrier, dissipation and friction then take you down to the bottom, and you've wasted energy roughly Kb log 2 on average. Log 2 is the entropy change in this system. So that is a truly profound relationship. It connects an abstract theoretical concept like entropy, Shannon entropy, one bit, to a thermodynamic cost of erasure. Now, it turns out there's a similar relationship for learning, and this is not very well known in the literature. I have a derivation of it in my a review paper in Contemporary Physics last year on the physics of learning, and it simply says that the change in energy of the switch is proportional to the change in average error per switch, and the constant proportionality goes as temperature. So if you think back to that XOR training curve I showed you, where initially the error was changing very rapidly and then stopped changing as the error got close to 0, you can see all the energy costs go into training, because as the error changes rapidly to begin with, or the power dissipation is large. And so this is completely analogous to Landauer's theorem, but for a learning setting. In fact, there's a deep connection, which I won't go into now, to explain why learning has to be like this, that comes from Landauer's principle. So the average energy dissipated per switch decreases as the average error decreases. So once again, you think, oh, great, I'll just turn the temperature down and I'll get the same error performance, but pay smaller cost in energy. But as we know, if you turn the temperature down, you'll eventually hit the quantum domain, and that's what I want to talk about a little bit now. So in the quantum domain, you can derive a similar theorem. Again, I only know one or two places where this is done in the literature, but it's a fairly simple argument. In the quantum case, as you turn the temperature down, you get a very different kind of relationship that doesn't involve temperature, but involves a quantum tunneling rate or a spontaneous emission rate or some other rate connected to a quantum noise process, some irreversible quantum noise process. But it's basically the same. So let me now talk a little bit about those kinds of devices. Oh, but before I do this, I want to just say something about the time domain. One tends to get the impression, looking at machine learning algorithms, that it's all discrete time, step by step by step. But in a physical setting, really what you care about are continuous time signals. So in collaboration with the University of Oxford, we're building some simple physical perceptron devices that work on continuous time. So this is a 2-bit gate with 2 inputs given by signals that are just square waves, 0 or 1 as a function of time. And the function I'm trying to learn is another square wave. That's just a label that tells you for each time slot what the output should be. And I run it through this physical neural network, and straight away you see what comes out is a very noisy version of what you put in. But nonetheless, you can easily see that you could train this device to learn a function by feeding back the actual noisy output to the true labels, which are deterministic, and try and minimize the energy consumption in the perceptron, which will guarantee it will learn just fine. Here's a simulation where we had it set up so that the weights were initially, well, I just chose some weight at random for this NOT gate, large positive number, and I set up the dynamics of the system so that it learns more or less instantaneously. It very quickly moves the weight straight to the learning side of the curve, and you can see that the output begins to match the correct input. This was for learning continuous time NOT, which I'll explain in a minute is a machine we can build right now, and in fact move on to XOR and other binary gates. Now this is perhaps one of the most important points I'd like to make. If you start off with a random weight chosen according to some thermal Gaussian distribution, the machine will learn by stepping back, and if you look at it from outside, it looks like it's cooling the weight distribution. What happens is you have this highly nonlinear stochastic process based on the feedback that drives the weights to a very narrow distribution centered on the negative side of the axis in the case of learning NOT. So from this point of view, learning machines are effectively cooling devices, and they cool in weight space. And this is a very important reason in understanding why machine learning is necessarily highly dissipative. So learning means cooling, very important point. And again, cooling requires a thermodynamic cost to be paid somewhere. It's a very complicated function that determines that in the case of NOT. Now you can just imagine how complicated this is going to get in the case of one of these big GPTs where you may have up to 1 trillion weights. The stochastic process in that weight space is just mind-bogglingly complex. Nonetheless, it'll work the same way. The feedback will drive the weights to be localized with some error on particular regions in weight space corresponding to the functions that you're learning. So the large learning models basically follow the same domain, but in a very complicated way. Here's another paper which connects the thermodynamics of learning to the actual information theoretical aspects of the problem. This is the only other one I could find that was clearly stated. Here they talk about the mutual information between the training labels and the actual output. And obviously you want to maximize the mutual information between the label and the actual learned label. And they show in this paper it's constrained by thermodynamic quantities connected with the rate of Shannon entropy in the weight distribution plus some heat dissipated per weight. This is a very important paper. These results are derived entirely using the stochastic fluctuation theorems of Jarzynski and Crookes, but in a continuous time stochastic process. Okay, so now let me move on to quantum learning machines, which, as I hope to suggest, I'll just see how we go, is really the future of quantum computing. So here's why quantum mechanics buys you a lot. As you turn down the temperature, eventually you'll get to the point where thermal fluctuations cannot take you over the barrier and learning stops. Fortunately, there's something called quantum tunneling, in this case quantum dissipative tunneling, which is now fairly well understood. which means that even though classically the process won't switch, quantum mechanically it still has a finite probability of switching. So now the switching is dominated entirely by quantum noise processes, and so long as that barrier is bigger than kT, this device is no longer a classical switch, it's a true quantum switch. And there are lots of these devices out there. We just tend not to think of them that way. It's a standard approach to measurement in superconducting devices, where if you want to read out a flux qubit or something, you pump it up to one of the excited states and watch it tunnel into some conducting state or some finite current state. Anyway, lots of current quantum computers work on, the measurement step works on this process. So here's what happens if you try to move continuously all the way from the classical switch to the quantum switch. You see what happens is that we get the classical Arrhenius law. This is a log scale. The classical Arrhenius law, which is just the Kramer's switching rate in a thermally activated double well. It eventually would keep going down all the way and just stop. But eventually, there's a quantum tunneling regime that switches on with a finite tunneling rate determined by how you've built this device, ultimately it's related to entanglement engineering in the reservoir. Likewise, the noise plateaus as well. So as we decrease the temperature, 1/T increases, and we eventually reach this regime here. So this is where we want to be to build a quantum learning machine. Okay, now let me talk a little bit about the experiments that I've been involved in. I'm not going to give too much detail on this. Here we have a quantum switch based on single electron tunneling in a surface gate defined quantum dot. So there are lots and lots of versions of these. This particular one is built by Natalia Ares at Oxford and Federico Fedeli, her research associate there. And let me just step through the various elements of this, because it's important to understand where is the readout, where is the actual switch, and so on. So this is looking down from above on metal gates superimposed above a two-dimensional electron-confined structure. And when you apply voltage to these gates, they tend to exclude electrons from that confined structure underneath, leaving a little puddle of electrons here. And these gates enable you to get to the point where you can only have 0 or 1 electrons on that dot. So you get to the point where the electrostatic energy is such that you can have no electrons on the dot, or at most one can jump on and be confined in the dot. The capacitive charging for the next one to come on is too big and won't be confined in the dot. It's basically a square well with only one quasi-bound state. Because electrons are charged, you need to take that into account if 2 electrons tunnel onto the dot. So that's my switch. It's going to be, is there an occupation of the dot or not? That's my quantum perceptron. Now, of course, I have to read that out. And so I do that by using what's called a charge sensor or a quantum point contact. So over here we have some bias between that side and this side, such that current can flow through this little channel here, and I can change the current that flows by putting a voltage on this gate here. I can shut off that channel completely, or I can leave it completely open. But more importantly, the voltage associated with the occupation of this dot can also change the conductance through this channel. So in many ways, this looks like a MOSFET, except it's not a metal oxide semiconductor, and it's not really a field effect transistor, but basically you have a device where a voltage here is changing a current through the quantum point contact. So this is the charge sensor here, and that's what we're going to actually measure. And we need to think about the quantum mechanics of that measurement process. We need to write down the stochastic Schrödinger equation and think about what that tells us about the occupation of the dot. Secondly, we need to think about the stochastic processes associated with the filling and emptying of the dot from the Fermi reservoirs on either side of this barrier here. So that's pretty complicated, and it depends on temperature, but it's all now very well understood. We can write down all the quantum stochastic processes associated with that. But from the point of view of the experimentalists, they just see either a low current through the quantum point contact or a high current through the quantum point contact. And so what they actually do in the experiment is feed back onto these voltage gates here. They become their weights, essentially, for a quantum perceptron to move backwards and forwards across the switching curve. And the width, the slope of this thing basically determines the noise and the learning rate in such a device. So the way it's done at the moment, oh, and the other key to point out, to be in this quantum dot rotation, you already need to be in the actual quantum domain, where the charging energy of this dot is 10 to the minus 27 joules, which at the 50 millikelvin or whatever it is they run in the fridge is much less than KT. So this device is intrinsically quantum. It's a quantum switch. It is irreversible and it is dissipative. Why is it dissipative? Sorry?
Much larger than KBT, or much smaller, much larger.
Oh, sorry. Thank you. Very important point. Oh dear. I knew I shouldn't have tried to do this on Sunday. No, never mind. Or Saturday. Yeah, much larger. The barrier height, B, has to be bigger than KT. Thank you. Where was I? Oh, yes. So what they do in the experiment, let's suppose they're trying to run this as a continuous time learning of binary knot. Pretty boring, I know. But to train a device to learn a logic gate, you have to give it the input together with the output. You don't build the gate, so to speak, which we all know how to do using transistor logic, but you just build an arbitrary switch or an array of switches, and you just keep feeding it inputs together with the correct output and keep feeding back until it eventually learns it. So in the case of NOT, it's really easy. You have a teacher gate and a student gate. One of this becomes a teacher gate and one becomes a student gate, and you keep monitoring this current so that eventually the current reflects what the control voltage is here and it basically inverts it. So you can turn this current then into a voltage and you have a continuous time version of NOT. You can clearly see if you extend this to 3 quantum dots, a triple dot, you can begin to move towards an XOR gate and so on. Now clearly this is not going to be scalable. It's not going to compete with 10 billion parameterized switches in reality. But I think you get the message that the quantum domain is indeed open to us. So in this case, the energy cost will always be much less than KT. Now it turns out there's an even better way to do this, and that's optically. So back in the early days of computing, before von Neumann entered the picture and sent us all off down the path of von Neumann architectures, there was something called the differential analyzer, which was an entirely analog machine. So the devices I'm describing here are analog. I'll come back to in a minute to explain a little bit why analog is important. But there's a better way to do it with optics, which is essentially a quantum differential analyzer. Oops. And it works like this. We're going to use the fact that we can make a Raman memory which can store a single photon pulse with different efficiencies depending on what the control pulse is. So we have a classical control pulse, just a coherent pulse, coming in here through an electro-optic modulator, and we have a single photon pulse with some temporal wave function. In this case, this is some Hermite Gaussian thing. It would probably be better not to try and put all your modulation in one time bin, but stretch it out. And the idea is the probability to load the photon in here, and you can always check, because if you don't load it, it comes out. And so this becomes your error channel, which you can now monitor. The probability to store the photon, modulo time constants and so on, is roughly this quantity here. It's the integral of the classical coherent control amplitude and the single photon control amplitude. Now, a single photon has 0 coherent field. It has no coherent field. Nonetheless, it's a truly quantum object. It's a massive superposition of excitations over many, many different energy eigenstates of light. But the key point that tells you this is quantum is it's the mod squared of this overlap function here. And so this now can be varied between 0 and 1, obviously, and you can monitor whether or not it's stored by looking at the output channel and simply feed back onto the electro-optic modulator in order to do the learning. And Ian Wormsley, my collaborator at Imperial College, is now building some of these things in his lab, not with single photons yet, just trying to perfect it using classical pulses. Now, classical pulses, it turns out, will never work. If you really want to reduce the energy cost, you've got to get the average number of photons per classical pulse down to 1. That means almost every pulse has nothing in it because the photons in a coherent pulse are Poisson distributed. So you really will eventually have to go to true single photon pulses in this device to do true quantum learning. But nonetheless, you can do proof of principle experiments in this way. Now, I mentioned the differential analyzer. Those of you who know about it will realize that this is essentially the key function that Claude Shannon used in his theory of general purpose analog computation back in 1945. It's the key component of differential analyzers, which are universal computing devices. is not widely appreciated, but there are universality theorems for analog computation, which Claude Shannon first outlined, didn't get it quite right, but have since been perfected, and we know the theorems. Basically, there's a class of differential equations you can solve that are equivalent to Turing computability. So analog computing is often dismissed. As I said earlier, the current race to build very efficient AI semiconductor devices is to go analog, to go to devices using memristors and where computation is as the same part of the chip as the memory. I'm not sure I mentioned earlier, but Sam Altman had a post recently on, in fact just this morning, on Perplexity, pointing out that Rain Neuromorphic has now got a massive injection of funding to build not optical neuromorphic chips, but a special kind of memristor-based chip to do learning. But ultimately, quantum optics will be the way to go to do this stuff at extremely low power. And this question of how to optimize it is discussed in this paper here that I wrote with my student Michael Cumming a couple of years ago. In this device, you can see the energy dissipated per switch is 10 to the minus 27 joules. At about a gigahertz, I'm thinking here of some optomechanical realization, and so the fundamental energy dissipation can be much less than the thermal dissipation. So let me now come back to the key point. The overall objective of this is to build a learning machine. And so now let me fill in the missing parts of the box here. Before I stressed that this is, enclosed in this box is our embedded autonomous learning agent, which is going to wander around the world figuring out what's what, or fly around the world figuring out what's what, or zip around the galaxy figuring out what's what, doesn't really matter. And it acts on the world and the world acts back. That's all it's got to go on. And it will only learn as much as those sensors and actuators will permit it to learn. From then on, what happens is this. Every time it pushes on the world from the primary actuator record, it sends a copy to a little emulation machine sitting in here, which is just the kind of physical learning machine I've been talking about. That learning machine will now try to predict what the sensation should be for that action. It then compares it to the actual sensation received from the world. So in this sense, this is an oracle-based learning machine where the oracle is the world, and so it's querying the oracle and trying to learn the function of the world. It compares that, and if they're not the same, it feeds back and starts changing the biases and so on in the emulation machine, and it just keeps doing this over and over and over and over again. So every one of these steps in here has been identified in the neuroscience of the brain. This mechanism here, where it pushes on the world and pushes on the machine inside, is called the corollary discharge in neuroscience. It's been known for 30 or 40 years. And in this case, this is a fairly deep issue here and slightly troubling for a physicist. It means the causal relations that this machine are learning refer to physical states of the machine, not to the world. In fact, it learns no more of the world than it knows through its primary and primary actuator and sensor records. So to what extent it's learning an objective fact about the world is an open question. I can answer questions on that later. Thanks. So, as I said, this is completely consistent with modern neuroscience. Here's Andy Clark stressing that the brain doesn't just sit there taking in data and processing information. The brain is not a computer, and it's not a digital machine, it's an analog machine. It's essentially continuously trying to predict and update very crude bits of information coming through its sensors. Likewise, N.L. Seth, who wrote a very powerful, famous book a couple of years ago called Being You, says the same thing. The brain works from inside out. It's always trying to predict the next sensation from a given action. And it builds analog learning simulators. They're actually based not on perceptron devices, but things related to clocks called spiking neurons. And it works by trying to predict what happens next. In fact, the title of Andy Clark's paper, the one I just showed here, is called Whatever Next. Rather nice title. So let me conclude. The learned functional relation between the internal actuator and the sensory reactions become the law of physics in this world. Could be really simple. Could just be learning XOR, kind of a boring world. But the world could be doing it with a Toffoli gate, completely reversible, but the machine will represent it as an irreversible gate. And we can learn something about the world via these learning machines and predict and change the world to our purposes. Now, I'm just going to hint at this in the remaining few seconds. Irreversible classical control is always measurement-based, so all classical learning machines will be measurement-based control. But in quantum control, there is a way to do feedback that is uniquely different. It is still irreversible, but it is not based on measurement. So what we're working on now is trying to design quantum learning machines that use coherent feedback. And so these are machines which will learn the world without any measurement result appearing anywhere in the record. And so such machines could quite possibly discover entirely new laws of physics, and they could construct new technologies. Unfortunately, they would be unintelligible to us. But given that, you know, the iPhone is pretty unintelligible to most people who happily fork over $1,000 for it anyway, that's not necessarily a showstopper for your business model. So let me come to the conclusion. As I've said, all learning machines are driven, dissipative, nonlinear systems. Noise is essential for learning. It's not a bad thing, like in current circuit gate-based quantum computing, which frankly I think is a bit of a dead end, is noise is essential, but it's got to be engineered. In classical learning machines, noise is thermal and turns off at low temperatures, but that's good, because now we can rely on quantum tunneling to get us through to the quantum layer. And finally, these things could discover laws of physics beyond our comprehension and build new technologies that we would never be able to build because of the kind of learning machine we are. Thank you very much.
So you'd mentioned the massive energy investment that the classical versions of this machine learning is requiring, and the quantum machine learning that you've been talking about, to my understanding, it still gets embodied in classical information, in the sense that, you know, we could, you know, you run your quantum machine learning and you get some result out, and you could potentially, you know, copy that 1 million times or 1 billion times and put it on everybody's iPhone.
You do get some classical information out.
I wanted to ask about the difference between that and something where the quantum ML result persists as, you know, a set of quantum states, so that it's not replicable, in the sense that you run through this machine learning algorithm with your quantum system, the information is retained as a quantum set of quantum states, and it's not replicable.
It is replicable because they're steady states. So in the case of quantum control, the machine will move to a quantum steady state, just like the classical machine, with cooling in weight space. So yeah, it's not a pure state. From the point of view of an observer outside, it's a mixed state, it's a dissipative steady state, but it's a fundamentally quantum dissipative steady state. It's essentially like a quantum phase transition that's occurring in the machine.
So I guess my question is that something that's replicable, or do you need to retrain every time?
No. Well, once you've trained it on the function you want it to learn, in this case, it's interacting with a chunk of the world. It will learn that chunk of the world and be able to... So once it's learned, it can move to what's called the control phase, which machine learning people call the inference phase. So long as it's working on the same chunk of the world, it will control that world extremely well. If it moves somewhere else and finds another chunk of the world, because it's a learning machine, it will just relearn the new function. And that's the whole point of learning. It just sees another part of the world, sees another bunch of oracle labels, and just relearns. So it is entirely robust up to the necessary noise required to learn, and it will function as a automated autonomous control machine.
Okay, thank you.
Time for one more question. Sorry. It's one more question. Okay, one more.
Can I go? Yeah? All right. Absolutely brilliant talk. It's really amazing. Thank you very much for doing this. My question is in relation to how somehow Rosenblatt original expression for the functional dependency kind of resembles Fermi-Dirac right? And then somehow it is optimal. Is there a hint on well, I'm not so sure about optimal, but is there a hint towards how can we inform now in the context of quantum mechanics, which you don't have to necessarily have that functional form?
Yeah.
What is optimal for learning in terms of this nonlinearity?
There is no optimal. Anything that goes from 0 to 1 in some nonlinear way is fine. It controls the learning rate. In an actual machine, that thing that I'm plotting there is not an average value, it's a probability, which is either 0 or 1 in any given realization. So all you need is a switch, which has a probability of not switching. And in the case of Fermi-Dirac, that's determined by underlying Fermi-Dirac statistics. But I have models which are entirely bosonic. We're just finishing a paper on a kernel-based quantum bosonic support vector machine, which is not Fermi-Dirac. It's based on continuous variable simulation. Yep.
Thank you.
Last question. Zach?
Thank you. Thank you. I had two questions, but I will reduce to one. Yes. Thank you very
Alexia,
much for
hello.
this. Yes. Hi. Thank you very much for the wonderful talk. The question that I want to ask is, this learning machine that you just presented to us, to compute the cost, you make the assumption that we start with quantum noise. But quantum noise doesn't come for free.
No, absolutely.
Quantum noise, you have to isolate your system and to bring, set up the stage for quantum mechanics to take place. And it comes with a classical context and everything. So how do you envision we could compute this cost without solving the problem of the measurement postulate, basically?
That's a very good question. Firstly, we don't have to solve the measurement problem because Natalia Arias has no problem making the measurements. So I don't want to be flippant about this, but in my opinion, it's only theoreticians that have a measurement problem. Experimentalists seem to be working just fine. Now, the substance of your question is this: how do I engineer quantum noise? And that requires engineering irreversible interactions between your local system, which is the switch, and its environment. And we're only just beginning to understand how to do that. So Howard Wiseman, for example, has some very nice models where he can get lasers with sub-shallow towns line width by engineering the irreversible interactions between the lasing transition and the bath, giving you the potential to have super accurate clocks beyond anything, as if we needed anything beyond what we've got now. But anyway, to give something much more accurate than what we've got now. So it all comes down to noise engineering. And having correlated noise in the bath is a resource that we can begin to exploit to control switching rates. So it's a very important question in understanding how we can control the noise required in quantum learning machines to achieve some particular learning rate for some particular objective. But I stress, ultimately, the costs are not set by the programmer, they're set by thermodynamics, quantum thermodynamics in the case of quantum learning machines. Ultimately, these are autonomous learning agents. And it turns out the best learning machines will be the ones that don't waste energy.